Thank you very much. A real pleasure to be here, and a real honor in the presence of all the distinguished guests, some of whom I met last time I visited Korea in December. So what I'm going to try to tell you about is the next revolution in AI. We've seen a number of revolutions in AI over the last 15 years. Deep learning sort of came to the fore a dozen years ago or so. More recently, LLMs and chatbots. But we're not done yet. We need a couple more revolutions before we get to truly intelligent machines. And in my opinion, as I've been saying for about 10 years now, I think it will come through this concept of world model. So I'm going to tell you a little bit about the motivation behind this and how we do this and what progress we've made over the last few years towards that. So first of all, why do we need AI systems that have human-level AI or more? And the reason is, in the future, maybe not too distant, all of us will be kind of walking around with wearable devices that will incorporate AI assistants that will help us in our daily lives. But currently, the technology is really not completely ready for that. I'm actually wearing a pair of smart glasses right now. I can take a picture of you, by the way. Smile. All right. I could have asked my assistant to actually take a picture of you as well. We need those systems to have human-like intelligence if we want the interaction with them to be easy for people to understand. And we need those systems to help us in our daily lives. We want them to some extent to be smarter than us in many ways. Many of us here are leaders in academia or the world of politics or business. And we're familiar with working with people who are smarter than us. I certainly am very familiar with the concept of working with people who are smarter than me. In fact, my entire job as a professor is to make my students smarter than me. So it's a wonderful thing to have a staff of people, whether they are real people or virtual people who are smarter than you. It just makes you, it empowers you. So that's what our relationship with future AI systems will be. They'll might be smarter than you, but they'll work with us, they'll work for us. But we need them to be understanding our world, etc. And we're not there yet. The technology we have is really not that good, and I hope you will pardon my French here. Current AI architectures really suck, in a way. They're nowhere near the kind of capabilities that we observe in humans and animals. Human and animals have mental models of the world. Their behavior is driven by objectives, or drives, if you want to call them, this way, and they can reason and plan complex action sequences. And we don't give enough credit to animals as to how smart they are. They really are smart. They're smarter than the best AI systems that we currently have. What we need really is, in our path to what I call AMI, Advanced Machine Intelligence. I don't like the phrase AGI that a lot of people have employed, because the G means general, and that implies that human intelligence is general, and human intelligence is not general at all. We're very specialized. In fact, we know we're specialized. In fact, the demonstration of this was shown here in Korea 10 years ago with AlphaGo. The experiments of this type show that AI systems can be superior to humans in a number of narrow ways. And that shows that humans are really not that general. So the concept of general intelligence is nonsense. But advanced machine intelligence, something that maybe would match human intelligence, is a good concept. So we need systems that understand the physical world, and current AI technology really does not. We need systems that have persistent memory. We need systems that can plan complex action sequences, systems that can reason, have long chains of reasoning, and we need systems that are controllable and safe. And current AI architectures have none of this, essentially, or only to a very small extent. So perhaps we can get inspiration from human learning and look at how babies kind of learn how the world works. When we're little, a few months old, we build a mental model of how the world works. And we do this just by basically observing the world initially, and then later by interacting with the world. But we learn basic concepts like intuitive physics, like the notion that objects that are not supported fall because of gravity. We learn this around the age of 9 months. It takes a long time. And so, again, how do we do this with machines? How do we get them to learn how the world works? By observation. And current architectures clearly don't do it because although we have systems that can pass the bar exam or solve mathematics problem and write code, we still don't have domestic robots. We still don't have completely autonomous level 5 self-driving cars. And the ones we have require a lot more than the 20 hours of practice that most teenagers would require to learn to drive. We don't have domestic robots to do tasks that a 10-year-old can do the first time we ask them without any learning, basically what we call zero shot. In fact, our AI systems, in terms of their understanding of the physical world, are not nearly as smart as a house cat. So that's the gap we need to fill. And this is a very old issue in AI. It's called the Moravec paradox, which, some tasks that humans consider complex, like playing Go or chess, or planning a path or something like this, are considered complicated for humans, but seem to be fairly simple for computers. But conversely, things that many animals can do effortlessly, we can't reproduce yet with machines. So the future of AI, I think, is more physical than the current one. And perhaps it's explained by this very simple calculation. A typical LLM, large language model, is trained with on the order of 3 times 10 to the 13 tokens, 30 trillion tokens. A token is typically 3 bytes, so the total amount of data for pre-training is about 10 to the 14 bytes. This is all the text that's publicly available on the internet, basically. It would take any of us on the order of 400 to 500,000 years to read. Now compare this with what a human child has seen in the first 4 years of life. The first 4 years of life correspond to about 16,000 hours of wake time. And we have 2 million optical nerve fibers getting to our brain, each carrying about 1 byte per second. Do the arithmetics, and that's about 10 to the 14 bytes. So a 4-year-old has seen more data than the biggest LLMs, but through high bandwidth sensory input like vision or touch or audition and other senses. And so that tells you we're never going to get to human-level AI by just training on text. We need AI systems to understand the physical world and train themselves through sensory input like video. There's a second issue, which is that we need AI systems to be able to produce their output through some sort of reasoning or some sort of search, not merely through a propagation through a fixed number of layers of a neural net. Okay? So LLMs and other systems basically compute their output by propagating a signal through a fixed number of layers of a neural net and then producing an output. But really, the way we humans and animals, many animals, reason is by thinking about something, but sort of manipulating a mental model and then searching for a sequence of actions that will accomplish a particular task that we set out to do. And so this is inference by optimization, not inference by forward propagation. And that's a very different concept that LLMs do not implement at the moment, or only in very trivial fashion. So, LLMs predict autoregressively. You feed them a sequence of discrete tokens, which may represent text or other things, and then you have them produce the next token, then you shift that into the input, and then produce a second next token, etc. There is some very basic fatal flaw with this. First of all, it is inference by forward propagation, where the amount of information that's communicated from one step to the next is reduced to basically 1 token, which is 3 bytes, typically. But there is the issue of, in fact, it's one of your papers, Jiajin, isn't it? Choi, right here. where you can show that this autoregressive process will diverge at some point. And there is really no way to fix this within the current paradigm. So one thing I've been interested in for a long time, over 10 years, more like 15 years, is how do we train systems to understand the physical world through self-supervised learning? So what has worked for text is that you, and it's the basic idea of self-supervised learning, you take a piece of data, you corrupt it in some ways. For example, you mask a piece of it, and you train a big neural net to predict what's missing in the input. And we could apply this to video, obviously, right? Take a video, show only the first part of the video to a system, and ask it to predict the remainder of the video. What is going to happen next in the future? And if a system is capable of doing this in any kind of reasonable fashion, it probably means it has understood something about the nature of the world. And I've tried to do this for a long time, but it didn't work until fairly recently. And so here's the basic generative architecture to do this, right? Show the beginning of a video, mask the future of that video, run the beginning of that video through an encoder, and then maybe a predictor. Perhaps that predictor is conditioned on an action that you know is taking place in the video, and then ask the system to predict or reconstruct the missing part of the video. And the problem is that this never worked. It never worked because, or it never worked very well. And the reason it never worked is that it's very difficult to predict all the details at the pixel level of what happens in a video. If I take a video of this room and I start from this side and I pan and I stop here and I ask the system, can you predict the remainder of the video? Of course, the system is going to predict at some abstract level that we're in a conference room and there are people sitting, and there's probably a wall at some point, and the carpet is continuing. There is absolutely no way it can predict exactly what every one of you looks like. It's an impossible task. It cannot predict the texture on the wall or on the carpet in detail, right? So the task of trying to predict at the pixel level is impossible. So, and in fact, when you do the experiment, this is some old papers from some of them for almost 10 years ago. When you train a system to do this kind of prediction, it makes very blurry prediction because it can't really predict what's going to happen. So it predicts a kind of an average of all the possible outcomes. And there are ways to fix this in various ways using things like latent variable models and diffusion models, but it's not producing really results that we'd like. So my solution to this is what I call joint embedding predictive architecture, or JEPA. And there's a whole community building around this idea of JEPA, although it's fairly recent. It's only 3 years old, roughly. But the idea is that instead of predicting at a pixel level, you train a system to learn an abstract representation of the input so that predictions can take place in this abstract representation space, not at the pixel level. So the two architectures are like this. On the left, you have generative architectures that all of generative AI is based on, produce pixels or text or whatever. And on the right, this JEPA idea, where both the observation, the X, and the variable to predict, Y, are run through encoders, and the prediction takes place in representation space. And to some extent, this is really at the root of intelligence, trying to find good representations of the world that we observe so that we can make prediction is at the root of intelligence, but also science. We do this in science all the time. I could explain everything in principle, everything that takes place in this room, going back to very fundamental physics, quantum field theory, right? If I could measure the wave function of this room, perhaps I could make some level of prediction about what is going to happen in the next few seconds, minutes, or hours by running quantum simulation. Of course, it's completely impractical. I cannot measure the wave function of this room, and there is no computer that's powerful enough to actually do this computation. So what do? We find abstractions that allow us to make those predictions. In physics, for example, or in science in general, we have a whole hierarchy of such abstractions. Particles, atoms, molecules. In the inanimate world, materials, objects, machines. In the animate world, proteins, organelles, cells, organisms, individuals, societies, ecosystems, right? And every level in this hierarchy is a different field of science. The field of science is almost defined by the level of abstraction at which we describe the part of the world that we want to understand. So this process of finding a representation so we can make prediction is really at the basis of science. For example, in thermodynamics, if we want to understand the behavior of, let's say, a box filled with some gas, we cannot make predictions in terms of the position and velocities of each particle. But what we can do is, at the global level, predict that when we compress, the gas is going to heat up, or when we heat it up, the pressure is going to go up. We have a law, PV equals nRT, right? The perfect gas law. So all of science is based on this idea that we need to find abstract representations that eliminate a lot of details about the observation that allows us to make predictions. So that's what JEPA really is based on. So this idea has sort of driven me to come up with some sort of AI architecture that might be based on this idea, which I call objective-driven AI systems. And I describe in a paper that I put online in 2022, A Path Towards Autonomous Machine Intelligence. And it's based on this idea of world model that I mentioned briefly earlier. What is a world model? A world model is a model that, given an idea of the state of the world at time t, and given a proposal for an action that an agent is imagining taking, can the agent predict what the state of the world is going to be at time t plus 1? And again, it's not going to be the full state of the world. It's going to be some abstract representation of the state of the world that contains the relevant details. So if we have such a world model, we can build an intelligent system that will be capable of planning, right? So we observe the current state of the world. That goes through a perception system that estimates the current state of the world, or at least the state of the world that we can currently observe. We combine this with the content of a memory that contains our idea of the state of the world that we don't currently observe, that maybe we remember. And then we feed that to our world model, and we feed also a candidate, a proposal for an action to take. And then we use our world model to predict the outcome of executing this sequence of actions. We can feed that to an objective function that measures to what extent a particular task has been accomplished or not. And then through search, we can search for a sequence of actions that actually satisfies this task objective. Okay, it's an optimization procedure of the type I was talking about earlier, and it's really akin to the type of planning and reasoning that humans and many animals are capable of doing. Now, in addition to the task objectives, we have to include guardrails, so things that will prevent the system from hurting people or doing stupid things or go beyond its design. And this is where safety comes in. This is, we're going to design safe systems by building them perhaps along this blueprint, but also designing guardrails that will make sure the system behaves properly. Some of us here in the room are interested in the application of AI to science, and this is really also a process we can use. There, the action in a scientific experiment is really an intervention. Can I predict what the state of a physical system is going to be by doing an intervention? This is really how you test a theory. And the test is to check whether the hypothesis is satisfied at the other end. Now, if we have a model of the world, we might want to apply it autoregressively, recursively, because if we have a model that can predict the result of executing an action, for a sequence, we can apply it repeatedly so that it can predict the outcome of a sequence. Now, the world, of course, is not deterministic, so this world model will probably have to get some latent variables which will parameterize the set of potential outcomes that may exist even in representation space. And eventually, we'll have to make those models hierarchical so we can do hierarchical planning. If I want to plan a trip, let's say I'm flying back to New York Thursday. If I have to plan my trip, I can't plan my trip from Seoul to New York in terms of millisecond by millisecond muscle control, which is really the low-level control variables in a human body. I have to plan at a higher level. I need to get a taxi to the airport and catch a plane. And so how do I get a taxi to the airport? Well, in Seoul Airport, you have to call one or ask the hotel to do that. If I were in New York, in my office, I could just go down on the street and hail a taxi. And then we can sort of hierarchically work our way down until we get to a point where we can execute the actions. So that's completely unsolved. There's a lot of work to do here in hierarchical planning. And the question is, how are we going to train those world models? Okay, and there's only, I don't want to go into technical details, but there is only two ways I know about to train such systems. And the key concept here is that we have to prevent them from collapsing. So collapse is the problem that if we train a system to find a representation and make prediction in that representation space, the easiest representation space in which to make predictions is a representation space that does not contain any information about the input. It basically just produces a constant representation, and that's not a good model. So you have to basically prevent the model from collapsing. And these two classes of method, contrastive and non-contrastive, I become a big fan of non-contrastive method, and I'll give you a few examples of those things working. There used to be contrastive methods that we use for self-supervised learning for images. That's going back to the early 90s, a paper of mine from 1993 about Siamese networks and some more recent work on this. But that turned out to be somewhat disappointing. What has turned out to work better is methods based on what's called distillation, where you really have two versions of the same encoder. So you take an image, you feed it to an encoder, and then you corrupt or transform this image, or maybe it could be a video that you mask, and you feed it to essentially the same encoder, and you train the entire system through a predictor to predict the representation of the original image from the representation of the corrupted or transformed image. That's a JEPA architecture. And one technique that works well is that you don't actually train the encoder on the right. You have it just use the weight of the one on the left, and you use that encoder as a teacher for the other one. And for some mysterious reason, it actually works. We don't completely understand why theoretically. There's a few papers on this, but it does work surprisingly well with some caveat. And in fact, it works so well that some of my colleagues at Meta have shown recently that this kind of method, a particular brand of method called Dino, actually works surprisingly well and beats all the approaches that are based on supervised or weakly supervised learning. The latest version is called Dino v3. It's open source, and you can just download it here. It's basically a generic image representation extraction that can be applied to a very wide range of vision applications, and it works really, really well for all kinds of tasks, and people are using them for all kinds of things from, astronomy to medical imaging to everything else. Now, with this type of method, Dino, we've been able to train a world model to do some planning. So essentially, on top of the Dino representation, we train a predictor that is conditioned on actions. It's trained from synthetic video of robots. And then we can use it for planning. So here's a short video that shows an example of this. The task here is to use a robot to push all of those little blue chips into a configuration that looks like the one on the top. So the top row is kind of a target state. And what you see at the bottom is a sequence of actions planned by the world model to, on top of the Dino representation, to push all those blue chips in their proper position. And it's a very complex problem. The underlying dynamics behind this is really complex. And we've applied this to a number of different situations where it seems to work pretty well, at least at some level of complexity. We're still working on this. Another one of our colleague, Amir Bar, has worked on a kind of a similar idea, except with a different encoder for navigation. He's a scientist at FAIR as well. And there, the purpose is to get a system to understand how the view of the world changes when you move. Okay, so this is trained with robot video. And you can basically tell it, okay, go to a place where you're in front of the door, or the red door, if you can see a red door. And the system can sort of plan a path towards the goal you give it, as long as this goal is visible in its view. It's been applied to a bunch of other things. This was presented at the last CVPR. Actually, you won some sort of best paper award. So this works well, but the question is, how do we train this JEPA architecture end-to-end? Basically by training the encoder together with a predictor. And there's some work that goes back a couple of years called iJEPA, where we train such an architecture together with the encoder to produce good representations of images, and we've gotten extremely good results on image representation. And more recently, we applied this to video, so it's called video JEPA. There was a first paper last year about this, and a more recent paper together with open source code and an open source model more recently. And it's a system that basically learns to fill in the blanks in a video. And it works very well for classifying various videos, but what's more surprising is that it's acquired some level of common sense. So if you show it a video where something impossible, unphysical occurs, like an object disappears or changes shape or something like that spontaneously, the prediction error of that system, the internal prediction error, shoots up. And so it tells you there is something impossible going on here. It's the first time I've seen a model completely self-supervised that tells you something impossible is happening in video. That's really how we actually try to figure out whether little children have acquired a concept. You see how surprised they are by a scenario that we show them. So that's a very interesting result, very, very promising. The VJEPA 2 model was recently released, and there's a version of this that is trained action conditions, so it can perform planning for robot and execute a number of tasks. And so I hope I have enough time to show you this video. So here's an example of this video JEPA model that was trained with sort of generic videos and then fine-tuned with action condition model, but not with this particular robot. And then it searches through a sequence of actions so that the world will look like the goal at the representation level, and plans the sequence of actions to, for example, pick up a cup and move it. Of course, you can do those tasks by programming the system or training by imitation, but this is essentially zero shot. You're not training the system for any of those tasks. It figures out how to solve them because of its mental model. This is really what we're after. So we have another set of techniques that we're working on which are extremely promising to train those JEPA architectures using it's kind of a measure of information. I'm not going to explain to you how it works but this is, in my opinion, the most promising aspect of it. So the challenge that we have is more theoretical, maximizing an information measure, and we don't know how to do this because we only have upper bounds and not lower bounds on the information measure, but we're still doing this. But let me conclude. I have essentially a number of recommendations for making significant progress in AI. Of course, if you want to work in industry, you have to work on LLMs because that's where applications are in the short term. But in the long term, we should abandon generative models in favor of those JEPA architectures, which are non-generative. Abandon probabilistic modeling because in this framework, probabilistic modeling really doesn't make any sense anymore. There is another paradigm that I've been advertising for a number of years called energy-based models. Abandon Kochati method in favor of those regularized methods, information maximization, which I only mentioned, didn't have time to explain. And of course, I've been saying for over 10 years, minimize the use of reinforcement learning because it's extremely inefficient. And I'm far from being the only person with this opinion anymore. So if you're interested in pushing AI towards human-level AI, you shouldn't really work on LLMs. You should work on the stuff that LLMs cannot do at the moment, which is this list of capabilities. So my prediction is that LLMs will become obsolete within the next several years, perhaps within 5 years or so. JEPA-style architectures will become prevalent, probably with inference through optimization. Real-time vision, I know there's a lot of people who are interested in hardware in Korea, so real-time vision will use a combination of things like convolutional architectures and transformers and various other things, but more is coming, so the search for better architectures is not over. And then for hardware, memory limitation, memory capacity has become a limitation, and I always had an interest in sort of exotic future technology like analog computation and things like that, but I've become extremely skeptical about it because we can't use hardware multiplexing as well as we can do with digital hardware. So with that, I'll thank you very much.
Thank you very much, Professor Lipkin, for your insights. So he had shared his views by giving predictions and recommendations. You can now return to your seats once you are done. Okay, thank you very much. And he introduced various technologies and systems